Okay, so we're going to talk about kinematics, and the first thing we need to talk about is displacement. And displacement is not necessarily equal to the distance traveled. So you've got this little example here that's basically telling you, look, you can have something flying all around and around and around, but if you have someone just going from point A to point B, they have the same displacement. Now, displacement is going to be, for instance, if I have a football player starting here, and they run around, they're trying to find someone to throw it to, and then they kind of backtrack, trying to get away. They're still trying to find someone to throw to, but they get tackled in this final position. Their displacement is going to be basically the resultant vector. Okay, and that's their displacement. If he were tackled the same spot that he was trying to, he first got the ball at, then his displacement would be 0. We also have to remember that it's always final minus initial, and that's something people often forget. So make sure you always do final position minus initial. When we get to acceleration, you do final velocity minus initial velocity. Very important. We will, again, have our positives and negatives, north being up and right, and will be positive, and south, down, left will be negative. We do have an average velocity. Every once in a while, we'll just have a problem that's just average velocity. So for instance, if I were to say I'm going to travel 100 kilometers, but for half of that trip, I'm going to do it at 50 kilometers per hour. That would take me an hour. And then I'm going to do the last 50 kilometers of it, but for some reason, I'm just going to really get faster here, kilometers per hour. I'm going to do that in half an hour. So totally the trip takes me 1.5 hours. Well, I've covered 100 kilometers in 1.5 hours. And so my average velocity is 67 kilometers per hour. Now, that's not usually what we're going to be doing. We're usually going to be doing instantaneous velocities, and the object will be accelerating. But every once in a while you have a problem that is just, this is just it. We are doing a constant velocity for this much distance, and just figure that out using dimensional analysis. What we're going to normally do is we're going to find our instantaneous velocity as our distance gets tinier and tinier and tinier and tinier and tinier to a point, and the time goes to 0. So our acceleration, notice when we do our acceleration, we're going to go final velocity minus initial over time. The units are meters per second minus meters per second divided by seconds, so the acceleration is going to be meters per second squared. It changes how much the velocity is changing every second. The acceleration is 0 if I'm going at a constant velocity. So just consider like a minivan versus a Porsche. You're going to have a better acceleration with the Porsche. It's going to be able to go 0 to 60 in much less time than the van does. It's not like the van can't go from 0 to 60. It can. You're just going to do it in a much slower time period. So we're going to talk about this negative acceleration here. In a position versus time graph, if I have a straight line here, the slope of this is constant velocity, and the slope is the value of the velocity. For those of you taking calculus, this is the first derivative. I have a positive slope, so a positive velocity. If you were to see something like this, you have an object that is not changing position. They're not moving through time, but not space. And if you were to have a negative slope, this is also a constant velocity if it's straight. The slope is negative, so the velocity is negative. We can also have position versus time graphs that show an accelerating object. So they'll be curved, and the slope tangent to a point is that instantaneous velocity. So I want to look at a couple of different slopes here. For instance, if I want to go from slow to fast. Now, this is a more shallow slope, so let's say that that is 10 meters per second. And this is a steeper slope, so let's say that's 20 meters per second. So for example, I would say my acceleration then is final minus initial over time. Let's say it's 1 second. and that's going to give me a positive 10 meters per second squared. Now, as I come over here, I've got a positive velocity again, positive slope, positive slopes. These are all positive slopes, so positive velocities. But I'm going, say, from a 20 meters per second, a steeper slope, to a more shallow slope. And so now what's going to happen here is I'm going to have my acceleration being final, it's always final, minus initial over time. And so I will end up with a negative acceleration. Okay. Now, we're going to look at another one here. This one where I have negative velocities. And I have negative because these are negative slopes. And so for here, I'm going from, say, a negative 20 meters per second. I'm slowing down to negative 20 meters per second. So my acceleration here then is going to be final minus initial over some time, let's say 1 second. So I will actually get a positive acceleration when I'm slowing down to the left. And again, these numbers, these negatives, don't worry about them other than we're going to the left, we're going south, we're going west, okay? That's all those numbers mean, the negative numbers mean. And so here, let's say that we're going from slow, negative 20, to fast, okay? My acceleration is going to be final minus initial over time. I'm not putting the units in there, but and what we're going to find here is we're going to get a negative acceleration speeding up to the left. So those are worth studying. All right, for some reason this is not doing, there we go. Oh, come on. I have a velocity one that we need to look at. I don't know why that's skipping that. Anyway. All right, so this one right here is a velocity versus time graph, so be careful. This is velocity versus time, t equals 0. Notice with these, I've got a straight line. This would be like the first derivative of that last graph. This is the first derivative, and I'm speeding up to the right, north, east, whatever you want to call it. Slope is the acceleration. It's a positive acceleration, so I'm going from like 0 to 10, positive 10. This is all above 0. So 10 minus 0 is going to give me a positive acceleration. Right here, if I have no slope, this is a constant velocity, 0 acceleration. And then if I would have a negative acceleration, my slope is the acceleration. I'm slowing down to the right. Let's take a look. If we go down here, let's say again, this is negative 10 meters per second. This is 0, going back to negative 10 meters per second. So again, I am going to have a positive acceleration if I slow down to the left, down south, because what's going to happen is I'm going to go 0 minus a minus 10 divided by however much time, I'm going to get a positive 10 meters per second squared. And here, if I go negative 10 minus 0 divided by 10, I'd have a negative 10 meters per second squared. The other thing worth noting here is that the area under the curve is the change in position of the object, the meters of displacement. So basically, you're integrating for those of you in calculus. Okay. Let's see. Yeah, okay. All right, let's take a look at one last one here. That is the acceleration, and this area under the curve here is the change in velocity for those who want to integrate. But the biggest thing here to realize is that it's a constant acceleration. It's your second derivative from the position versus time graph. If you want to change A, it's actually called a jerk. That's the third derivative. It'd be like in meters per second cubed, and trains and stuff try to keep the jerk under like 2 meters per second squared for comfort. All right, so these are the kinematics, and kind of explain to you where they're coming from in the graphs. This looks like your position graph. This is your position versus initial velocity times time plus time squared. This is a quadratic formula, and if you take the first derivative, you're going to get this. Okay, this is integrating a velocity versus time graph, and this can also be derived by calculus, or you can do substitution where you take time is equal to that and then substitute it in here and do some algebra, and you can get that too. So these equations are going to indicate distance is going to be x. X is distance or displacement, I should say. Initial velocity, final velocity, and time, and your constant acceleration. All right, we're going to do one problem here. We have a tennis ball going 7.8 meters per second to the right. Rebounds, so my initial velocity is this. My final velocity is negative 6.5 meters per second. And our time is 0.015 seconds. So you're trying to figure out what your acceleration is. Now if you look at your kinematics, you just basically look and see which one is going to work for you. Now you don't have a displacement, and so any of those with x in them really isn't going to be the one you want. What you're going to probably want is the second one here, which is really what we looked at for acceleration. We said acceleration was final minus initial over time, so it's just a variation of that equation. So to find your acceleration, you're going to say final minus initial over the time. And the units are going to be meters per second, and seconds, and you are going to get negative 953 meters per second squared. So quite the acceleration.